So I thank all the people who came to ask me questions. I encourage more of you to come and ask questions because that's what I'm here for this week. So please do. Yesterday we discussed supersymmetric QCD, and we discussed it in the limit that the mass was much bigger than lambda. And we derived some expectation values. For the meson, this was the bilinear, which was dead m, eta, to the power 1 over nc, 1 over m. And the Gauge-Inu bilinear, which was dead m, eta, to the 1 over nc. And I think I had a typo in one of these equations yesterday on the board, so I think these are the correct ones. And we explored some of their properties, which some of them look strange, like when the mass goes to 0, depending on the number of flavors and colors, this thing could be quite singular, or could be ambiguous. And we could also perform some Legendre transforms of that. And in particular, I would like to focus on this guy that depends only on big M. And we mentioned some peculiar properties of these things. For example, if we just take the determinant of the top guy, it's typically non-zero, unless the mass is special. And yet, if you remember that the meson M is a bilinear in the quarks, the rank is at most NC, and therefore if NF is bigger than NC, this seems like a contradiction. The other thing is that when the number of flavors is less than the number of colors, no matter how we take the limit, the expectation value of big M always diverges, which looks strange, because this is a theory of matter. How come we get infinite expectation values? And finally, if we turn off the mass for a larger number of flavors, depending on how we take the limit to 0 mass, we get different answers, which also looks strange. So in order to understand all these three properties more carefully, we should go back to the classical theory and understand the classical theory. For m equals 0. So if you just look at Wesson-Bagger, we see that there is a scalar potential, which is proportional to the sum over the generators of the gauge group, dA square, which is equal to the sum over the generators of the gauge group, trace q ta q dagger minus q tilde star ta q tilde transpose 180 square. So every one of these terms here, we contract the color indices, and the trace does the sum over the flavor indices. This is the contribution of the quarks q, and these are the contributions of the anti-quarks q tilde. And for every gauge field, we have such a D, and we just sum over the generators in the gauge group. So this is the potential. It's purely cubic, it's purely quartic. And we notice that it has flat directions. So let's see, we want to solve this equation equals 0. So V equals 0 if and only if we can solve dA equals 0 for all A. And for NF less than NC, we can solve them as follows. Up to various symmetry transformations, we can put V1, VNF, and 0 here. So this is a rectangular matrix. Flavor runs this way, color runs this way. There are more colors than flavors. And up to symmetry transformations, gauge and global symmetries, we can always bring the matrix Q to this form. And if we take these rectangular matrices and we just plug them here, we see that whatever contribution we get from here is exactly cancelled by that one. So that means that the potential is 0. Notice that so that means that semi-classically, the theory has not just one ground state, but an infinite number of ground states, labeled by these parameters V1 to VNF. we can give a gauge invariant description of all these expectation values by constructing our meson Q tilde Q transpose. This is a matrix in flavor, the same M that we had before. And the ground states are in one-to-one correspondence with this M. So again, the space of solutions of the D-term equations, modulo gauge transformations, is given exactly by the space of M's. Now, let's see semi-classically what such a ground state is. Generically, that is, if all the V's are generic, non-zero, no two of them are equal, and so forth, the gauge symmetry, which was SUNC, is spontaneously broken by these expectation values to USUNC minus NF. Because as I said, color acts this way, and here we have 0, so we can still have freedom to act here. This is still an unbroken symmetry. We see from here that these ground states are inequivalent. So you'll learn about spontaneous symmetry breaking, where we have a symmetry that acts, say, on pions, and we get a manifold of ground states, points related to each other by a global symmetry. Here, these points are not related to each other by a symmetry. This is very common in supersymmetric theories and very uncommon in non-supersymmetric theories. We have such an accidental degeneracy among ground states. In non-supersymmetric theories, we rarely have that. In fact, you have learned that already in quantum mechanics. In quantum mechanics, if we have two levels and we dial the parameters in the Hamiltonian, the two levels might cross each other. One of them will get higher, one of them will get lower, and at some points they will cross each other. But if you remember from your quantum mechanics class, this never happens. Instead, what happens is the levels tend to repel each other. And instead of crossing each other, they go like that. In other words, in quantum mechanics, it's very rare to have two levels, two energy levels that are not related by a symmetry being degenerate. This is extremely rare. In supersymmetric theories, this is extremely common. Basically, the quantum fluctuations that will try to remove the degeneracy, these quantum fluctuations cancel between bosons and fermions. We'll see that in more detail soon. One way to see that this ground state is inequivalent is we can turn off, say, one of these guys, say the last one, and then the unbroken symmetry is not SUNC minus NF, but there is a +1. The broken symmetry becomes bigger. So this is just an example that these points are not related by symmetry. So having such a potential that has flat directions where we can go run off to infinity is a good starting point for answering the first question we asked. Because if I said yesterday, and I repeat it today, that when the number of flavors is less than the number of colors, if I turn off the masses in these exact expressions, the expectation value of big M can run off to infinity. Now we see a very clear physical way this could happen. It happens because the potential has these directions that M can run off to infinity. It would look very strange to have a theory that has potential that rises in all directions and get some expectation values being infinite. This would be very hard to understand. But having such flat directions in the potential gives us the option of running off to infinity. I'm not going to discuss here what happens when NF is larger than NC. The analysis of the vacua is a little bit more complicated. But let me continue to ask quantum mechanically what happens along these flat directions when the NF is still less than NC. So the first question we should ask ourselves is the vacuum degeneracy lifted? So we have this vacuum degeneracy, inequivalent vacua, and we can ask, can this be lifted somehow? Well, if we want to lift the degeneracy, we'd like one of them not to be a ground state and the others maybe to remain ground state. We'd like to lift this thing. How will this happen? This will happen only if we have some kind of a potential on that space. So we should look for a potential a superpotential or potential V effective along the flat directions. And And since the theory is supersymmetric, the way to do that is to have an effective superpotential. Since the only light field is M, we should look for a flat direction for M, some superpotential for M. And now we are going to use our rules from yesterday. Whatever we write has to be holomorphic in M, holomorphic in eta, and should respect all the symmetries. And in perturbation theory, we have a lot of symmetries because eta is not charged in perturbation theory. There's no eta is not charged, and therefore, in perturbation theory, and therefore, without doing any work, we know that we can calculate all day in perturbation theory, go to very high orders. We're never going to find a superpotential. This is essentially the same non-renormalization theorem we had yesterday. And since we're not going to find any superpotential, we're not going to find any potential, and therefore, the vacuum degeneracy is not going to be lifted. So this is a statement in perturbation theory. We have an accidental vacuum degeneracy. Points are not related to each other by a symmetry. What happens non-perturbatively? So I had yesterday this little table, and I said that the principle, the guiding principle, is this no miracle principle. We should just go after the symmetries. So in perturbation theory, we had this axial symmetry that is anomalous, and we could still use it in perturbation theory. But non-perturbatively, the anomaly is activated. Non-perturbatively, this guy eta carries charge. And therefore, non-perturbatively, we can allow for W effective that depends on M and on eta. And now we have less symmetries, and therefore we have less constraints. And if we have less constraints, maybe there is a term we can write down. And the answer is yes, there is a term. In fact, this is precisely the term we discussed yesterday, except that now the interpretation of this term is different. The term that can be generated is eta over det M minus NF. So yesterday, we derived that when the mass is big, such a term is generated. In fact, it's written here. But the interpretation was totally different. Here, M is a composite operator in the theory. And that's valid when the mass is big. Now we are analyzing the theory when the mass is small, and M is a coordinate on the space of vacua. The space of vacua, by the way, is also called moduli space of vacua. So we have a space of vacua parametrized by big M, and we ask, can there be a superpotential along this space? And we haven't yet proven that this term exists, but whatever can be generated must be this one, because no other term is invariant under the symmetries. No other term respects our three rules of symmetries, holomorphy, and various limits. So what remains to be done is determine the coefficient. In fact, we already expect such a term to be present, first because of the no miracle principle. Whenever something is allowed, it is generated. And second, because we've already seen in the other limit that this term is generated. But let's continue this line of reasoning and argue that this term is actually present. So I'm not going to do it in a lot of detail, but I want to argue that there is one situation where this thing is particularly easy. And this is the case when the number of flavors is one less than the number of colors. So in the special case, where the number of flavors is the number of colors minus 1, various things happen. The first thing is that the SUNC gauge group is completely broken by the expectation value. So what are we doing? We're going far out along the flat directions, very large very far away in field space, at very large values for the fields. The theory of C is the UV theory Everything is weakly coupled, so we should be able to use semi-classical techniques. So the first nice thing about this case is that the gauge loop is completely broken. There is no fancy strong dynamics in the infrared that we have to deal with, because all we see at long distance are these chiral superfields M. The second nice thing that happens here is if we just look at what we would like to get, the fractional power is gone. So we should expect an answer proportional to eta. And we already said yesterday that eta is a one instanton factor. It has exactly the real part in the exponent e to the minus 8 pi square over g square, characteristic of instantons. And the theta dependence is exactly e to the I theta, because it carries exactly 1 unit of topological charge. Yes?
Above we said SU and C gets broken to SU and C minus NF. Shouldn't then this be broken to U1? SU1.
There is no SU1. There is no such group. Sorry? I'm sorry?
Okay, sorry.
So in this case, the group is completely broken. And this is precisely the only situation where instanton methods are actually reliable. When there is strong coupling, there is non-abelian gauge dynamics, which is strongly coupled, instanton methods are not reliable. So fortunately, the answer we expect proportional to precisely eta, which is the hallmark of one instantons. And you see, this is really strange, because the fact that in this case, and only in this case, the gauge group is completely broken, this follows from this form of the expectation value, which follows from the form of these D-term equations. So we had some D-term equations, and we diagonalized a rectangular matrix, and we found this thing, and that tells us that the gauge group is completely broken. Precisely at this point, something else happened. The charges constrain us to have something of this form, and precisely for NF equals NC minus 1, there is no fractional power, and the thing is proportional to exactly 1 power of instanton, which means 1 instanton. So it's 1 power of eta, which means that it's a 1 instanton effect. Notice that two totally different lines of reasoning tell us that this should be the interesting case. Now, I'm not going to do it here in detail, but an explicit instanton computation shows that the coefficient here is indeed non-zero and determines the coefficient. And in our normalization, it will be exactly 1. Now, this is quite significant because it closes a lot of gaps. Gap number 1, we talked about the non-renormalization theorem that is valid perturbatively. Now we see that the naive non-renormalization theorem, namely superpotential is not corrected in the quantum theory. This thing is not correct non-perturbatively. Non-perturbatively, instantons violate the non-renormalization theorem. This is the first significance. The second significance is that it demonstrates our no-miracle principle, that there is a non-renormalization theorem in the non-perturbative theory, which allows only this term, and once this term is allowed, it is indeed generated. So there was no magic that gave us 0 for no good reason. This thing was allowed, and therefore it is indeed there. There was a question here? No. The next point that is significant about that is that once we established that the coefficient here is 1, I can replace this squiggly line with 1, we can now give masses to some quarks and derive the answer for fewer flavors, because now we don't need to do any more computation. So we can start and give masses to some quarks, so we get eta over det m. Little m, big M. And we can take this little m to be a matrix, m1, stop at some number, and put zeros here. and just solve the equation of motion of the corresponding components of big M, everything that is in here, in big M, and derive an effective Lagrangian for the light degrees of freedom. So using that, we can integrate out i.e. solve equation of motion of components of M, and derive an answer for fewer flavors. So the answer for NF less than NC now becomes the same answer we had before, NC minus NF. So this now becomes a result of a computation. And not only a computation, it's a computation with a normalization. And we can go all the way to the end and, if you wish, run the arguments of yesterday backwards and determine all the normalizations in all the coefficients in all the expressions. Remember that yesterday I assumed a lot of facts about the pure gauge SUN gauge theory, that there is a gap, there is chiral symmetry breaking, and the normalization is exactly 1 in particular subtraction scheme. Here, this is the only place where we need to do an explicit computation. It's enough to do an explicit computation in one case, and this computation is a semi-classical computation, so it's straightforward. Might be tedious, but it's straightforward. And once it is done, it trivially determines all the coefficients with all the normalizations everywhere, and it justifies all the assumptions we made. So there were some questions here. Yeah? Well, the references I gave yesterday, the 2 reviews I wrote with Intelligator, have everything. There's also a book by John Turning, which I think gives a little bit more detail.
I was wondering if there's been explicit calculation done for the NF small n case and what this fractional is.
I'm going to explain that now. Good question. So somebody could ask, not only could ask, somebody has just asked, precisely this question. How can we understand this term from the low energy perspective? So one perspective is to start with NF equals NC minus 1 and integrate out stuff and derive this term. But we could ask, can we just get this term on its own? Can we understand the meaning of the fractional power? So let me do that. So I've already said that for NF less than NC minus 1, so let's say less. So that the gauge group is broken to so now the low energy cast of characters are the components in M and the components of these gauge fields. So now a low energy observer sees semi-classically the same matrix M of chiral superfields and this gauge group. And nothing is charged under the gauge symmetry. So to leading approximation, we just get the dynamics of this gauge group. And what is the scale of this gauge group? This gauge group has its own eta L, and it's related to eta and determinant M. And if you do the calculation, eta M is exactly that. So this is very similar to a computation we outlined yesterday. The scale of the low energy gauge group is determined by the scale of the high energy gauge group and this expectation value that breaks the symmetry. So what do we have? At low energies, we have this gauge group. It becomes strongly coupled, and now we turn the crank again. It becomes strongly coupled, it produces a gap, it breaks its own chiral symmetry, and it creates a superpotential, which is the number of colors, NC minus NF, eta low to the power 1 over the number of colors, which is NC minus NF. So I'm just using the same formulas we had yesterday, and lo and behold, we get exactly the same answer. So the fact that we get the same functional form should not be surprising, because this is the only allowed functional form consistent with the symmetries. So that we shouldn't be surprised. The fact that normalizations work This is a nice consistency check. So now we see that everything hangs together. If all the masses are very big, we derive this answer one way. If all the masses are very small, we derive the answer the other way. So altogether, we now understand what the interpretation of this formula is in the various limits. And we also determine the coefficient. What are the consequences of this superpotential? When the mass is small, the classical potential is a good approximation. We have these flat directions. And the first correction along the flat directions is this superpotential. So let's plot it. So classically, and to all orders in perturbation theory, the potential was exactly 0 along the flat directions. What happens non-perturbatively? Well, we found some superpotential. We should also ask ourselves what's the Kähler potential, and once we have both the Kähler potential and the superpotential, we can calculate the answer. So the Kähler potential can be determined semi-classically. So it's approximately given by the classical answer. And if you just do a little bit of algebra, it's twice trace m dagger m to the 1/2. So this is the classical answer for the Kähler potential along these flat directions. We can introduce, there could be perturbative corrections. They are small because when m is large, the effective gauge coupling G is small, and therefore all the corrections are small. So let's just take this classical formula, use it with this superpotential to derive a potential that looks like this. So again, classically, with 0 mass, this is the potential. Classically, with small mass, so this is V classical when m is non-zero. The potential with 0 mass is this. And when the mass is non-zero, all we need to do is take the superpotential that we derived, add the mass term, and find the potential that looks like that. So you see what happens. We have a competition here between the classical potential associated with a mass that tries to push us toward the origin and the dynamical superpotential that tries to push us to infinity. And we find some supersymmetric ground states here. And they lead to the expectation values written above there. And you can easily do the algebra and determine the answer. As we turn off the mass, this minimum runs off to infinity. So to summarize, the classical theory had an infinite number of ground states, a continuum of ground states. And the quantum theory, for 0 mass, has no ground state at all. We only have runaway behavior to infinity. So for non-zero m, we have NC vacua. And for m going to 0, we have runaway. To infinity. Thus explaining this thing we saw before, that if we take the exact answer that we derived in the other limit, we derived it in the other limit and we argued that it's exact, and we found that the expectation values run off to infinity, now we see why it happens in the limit that the mass is small. Now, this is one example that I worked out in some detail, but it turns out to be rather generic. And many of the points that I've pointed out in this example, as I went through the analysis, appear all over the place. The notion of modular space of vacua in the classical theory, whether they are lifted or not lifted, runaway behavior, all these things occur all over the place both in field theory and in string theory. And it's good to have at least one example in mind where every single thing is calculated and is calculable with all the coefficients, so we really know what we are doing, because it always guides our intuition. But this cannot be the whole story. It cannot be the whole story, because if we look at these expressions, this expression, which is the answer we would like to interpret, does not make much sense when the number of flavors is bigger. In other words, we still have a moduli space of vacua when the number of flavors is bigger. The number of flavors is bigger, we still have a modulus, classically, moduli space of vacua. And we can say, well, maybe the same thing is true. This term respects all the symmetries, so maybe it is generated using our no miracle principles. Whatever is allowed should be generated. Well, a little bit of inspection tells us this cannot possibly be true. First of all, for nf equals nc, this is infinite, and this is the prefactor is 0. So this expression doesn't really make much sense. Second, along the flat directions, so the same object M here has two different interpretations. First, it's a coordinate on the flat directions, where classical physics is valid, and therefore this formula is true. Its rank is constrained. Second interpretation, this is a composite operator in a quantum field theory. This formula is not true, and indeed we know that the expectation value has higher rank. So if we ask ourselves, what kind of a superpotential can we write on the flat directions? The answer to this question should involve an M that satisfies this constraint. And if this constraint is satisfied, the determinant of M is 0, and therefore this expression doesn't make sense. This expression is singular. In other words, when we use our general rules, we write the most general thing that can be generated, subject to the symmetries and so forth. We conclude that no superpotential can be generated. This is interesting and surprising. I've just argued that this peculiarity of inequivalent ground states exists classically and persists to all orders in perturbation theory. But non-perturbatively, this peculiarity is not true in the quantum theory when the number of flavors is small. Now I'm arguing that when the number of flavors is larger, this peculiarity is true in the full quantum theory, even non-perturbatively. So this is even a more powerful non-renormalization theorem. And therefore, modular space of vacua in the full quantum theory. Exact, non-perturbative, flat directions. This is even more surprising than the previous result. We have a fully complicated quantum field theory, and it has flat directions, classically. And then, depending on the number of flavors, this degeneracy, this accidental degeneracy, is or is not lifted. And if the number of flavors is large enough, specifically larger or equal to the number of colors, then whatever we saw classically remains true quantum mechanically. Namely, we still have all these flat directions in the potential. The vacuum degeneracy is not lifted. So this begs the following question. What is the meaning of this expression we derived? So yesterday we derived this expression in the limit that the mass is big. We reinterpreted it today in the limit that the mass is small. The limit that the mass is small, we said, okay, this is a superpotential generated along the flat directions, and it lifts the degeneracy. Now we see that when the number of flavors is bigger, this interpretation cannot be true. Even more than that, if you look when the number of flavors is bigger than the number of colors, we have an eta here. This is this instanton factor. So notice that what do we have in the numerator? We had in the numerator eta to the 1 over nc minus nf. And that goes like e to the minus 8 pi square over g square, 1 over nc minus nf. But this is negative. So this scales like e to the plus some number over g square. So it's not even non-perturbative. It diverges in the classical limit. So this object looks very singular in the classical limit. So it really begs for an interpretation. So you see what happens. Yesterday we derived this result in one limit. This result makes a lot of sense for small number of flavors, but it makes no sense when the number of flavors is larger. So I'm going to give now the interpretation of this fact and many others. Are there any questions before I give the interpretation? Is it clear what the puzzle is? We derive something in one limit. In some situations, we can explain it in the other limit. In the other situations, it has no reasonable interpretation. So I'm going to state the answer now. And I'm not going to prove it. I'm just going to state it. And I'll outline some consistency conditions that can be done. And many of them you can do yourself as exercises. But what's more important, I'd like to really highlight the important qualitative consequences of this result. So we now specifically on NF bigger than NC. And I'd like to argue that the same theory that we had has another dual description, which is also of this kind, where the gauge group is SU NF minus NC, and it has NF flavors of quarks and antiquarks, not to be confused with the original ones, and the gluons of this theory should not be confused with the gluons of the other theory. And there's also an elementary field M, and there's a superpotential, and for normalization, I will not even worry about the normalization here. You can read more details about the normalizations in the literature. So this statement looks very strange. We started from a gauge theory. It becomes strongly coupled in the infrared. We don't know what it does. We know that the vacuum degeneracy cannot be lifted. And I claim that it is dual to this theory. There is a special case that might deserve an explanation here. So I'll first get the special case out of the way. Somebody asked me about SU1. We could ask the same thing here. What happens when this thing is exactly 1? Okay, we won't do that. You can read about it in the literature. I'm running out of time. So what does this thing mean? First, the kinematics. We have two different theories. If we claim that they are the same, at the very least they should have the same global symmetries. So it's straightforward to check that these two theories have the same global symmetries. And the quantum numbers of this M which is elementary in this theory, are the same as the M that we had before that was composite. So now we're slowly going to work out the dictionary between the two theories. And this M here, which is an elementary field, is a composite field in the original theory we started with. And these two theories have exactly the same symmetry. Each of them has an anomalous symmetry. The anomalous symmetries do not match, but the anomaly-free symmetries do match. So this is the first test. That's an easy one. There's a slightly more sophisticated test associated with anomalies. When we have global symmetries, they have netter current. And we can compute the triangle diagram for 3 currents. Even though the symmetry is conserved, the triangle diagram can exhibit an anomaly. And this anomaly is something that is universal for this theory, and it's determined exactly at one loop. So we should be able to do this one loop computation in the 2 different theories. The 2 theories have totally different perturbation expansion, totally different set of fields, but these anomalies should be exactly the same. This principle was first put forward by 't Hooft in the late 70s. I think it was 79. And the 't Hooft matching conditions also work. So this is the second test. The second thing we can do is turn on a mass. If we turn on a mass in the original theory, we do that by adding mq q tilde. We turn on a mass, and what it does is reduce the number of flavors by 1 and does not affect the number of colors. In this theory, we just add trace nm. So what appears as a mass term in the original theory that I'll call electric, in this theory that I'll call magnetic for reasons I'll soon explain, this is a term linear in m. So notice what it does. We have this 3-level superpotential, and imagine we turn on such a thing. Then W now has m q q tilde plus m m. And now the equation of motion of m tells us that q q tilde equals minus m, and I'm suppressing indices. So this gauge group that I'll call the magnetic gauge group is now broken because q is non-zero. So little q is non-zero. And the SU NF minus NC gauge symmetry is broken. Exactly what it is broken to depends on what kind of mass term we turn on. What's the rank of this mass matrix? And we can check, I've almost done 90% of the work here, that if we had some number of flavors and colors in the electric theory, and we turn on mass, we reduce the number of flavors, say, by 1, not changing the number of colors. This translates here to the same thing. So more mathematically, there's a commutative diagram, 2 dual theories. We turn on the same operator on both sides, and we find, again, 2 dual theories. We can actually do this in a little bit more detail. And imagine we explore the region in field space where M is generic. So we go to this theory, and we just explore the region in field space that M is generic. Notice that the rank of the matrix of this meson field M is not constrained here because it's an elementary field. So when it is generic, it gives masses to these quarks. And once it gives masses to the quarks, we can again do the same calculation we've already done 3 or 4 times here in different contexts, integrate out all the quarks, and have, so all Q's and Q tildes are massive. With mass proportional to big M. And now we have gaugino condensation in the magnetic gauge group. And it leads to a superpotential, which is precisely the one that we needed there. So notice how this thing resolves two of the puzzles we had before. First of all, the rank of the matrix M is unconstrained. It could be as large as we want because it is an elementary field. And second, when M is generic, we give masses to the quarks, and Gaugino condensation in the magnetic theory gives us this expression. And all the puzzles we had here, the dependence on eta and all that are gone because all that happens in the magnetic theory. So these are kind of simple tests, but I'd like to give a little bit more detail about the meaning of this whole thing. And the interpretation is again different depending on the number of flavors and colors. So imagine the number of flavors is less than 3 times the number of colors and larger than 3.5 times the number of colors. So because of that, the electric theory we started with is asymptotically free. So as we go to the infrared, it becomes more and more strongly coupled. So the electric theory is UV free. Start with the theory of gluons, and it goes in the infrared somewhere. We're soon going to say what it does in the infrared. In that range, if you just substitute it in this with this number of flavors and this number of colors, and again use the same bound of asymptotic freedom, the magnetic theory is also UV free. So in the UV, these two theories are not identical. We have two different gauge theories. Both of them are UV free. As we flow to the infrared, both become strongly coupled, and they flow, I claim, to the same point. So this duality is not an exact duality. It's only exact in the infrared. The long-distance behavior of these two theories are the same. And what's the physics of this point? At this point, claim we have a non-trivial interacting CFT, also called Banks-Sachs in the literature. Let's see how we can understand that in the electric language. So let's plot the beta function as a function of the gauge coupling in the electric variables. We start with 0, and the beta function is negative at one loop. So the coupling constant goes like that. The beta function looks like that. And the coupling constant starts getting bigger and bigger as we go to the infrared. The sign of the two-loop beta function is positive. So the beta function looks like that. So the renormalization group flow starts here in the UV and stops here in the IR. So this is the direction of the renormalization group flow. So the theory, if the number of flavors is close to the top, is close to 3 NC, the gauge coupling starts running, and immediately the two-loop beta function kicks in and stops the running, and the theory stops at a non-trivial fixed point. This is an interacting conformal field theory. During the last several years, there was a lot of discussion of such conformal field theories. We know quite a lot about them. And this is one of the most common examples in 4 dimensions. So this is a non-trivial fixed point in 4 dimensions. Now let's crank the number of flavors smaller. If the number of flavors is smaller, already at 2-loop we see that the 2-loop effect is going to be a smaller effect. Sorry, it's going to be a smaller effect here, but it's going to grow. And for fewer flavors, it looks like that. So as the number of flavors is cranked down, the fixed point occurs at larger and larger values of G, and therefore it's more and more strongly coupled and more complicated. And the anomalous dimensions differ from the anomalous dimensions of the free theory by larger amount. So that's on the electric side. What happens on the magnetic side? There's a very similar picture. It also looks like that. But here, the fixed point is weakly coupled. And here we have the magnetic G is much less than 1. And here, for NF less than or approximate 3NC, the electric coupling is much less than 1. So notice what happens here. As the coupling, as we start for very large number of flavors, close to 3NC, the electric description gives us a weakly coupled description, which is very good at the fixed point. As the number of flavors becomes smaller, the value of the coupling constant at the fixed point becomes larger, and the weak coupling picture is less and less accurate. But as it becomes very, very strongly coupled, the magnetic description takes over, and it becomes a good description. And the fixed point of the magnetic theory is approaching 0 at the fixed point. So this is what happens here when the number of flavors is in this range. This range is referred to as the conformal window. And when this thing happens, we have two different theories flowing to the same fixed point. And in the language of the renormalization group, this is called universality. These two different theories are in the same universality class. And we have tons of examples of that in 2 dimensions, in 3 dimensions, and this is an example in 4 dimensions. It's a lot more dramatic when the number of flavors is smaller. In this case, the magnetic theory, so the electric theory is even more strongly coupled, and it's hopeless to understand it. But in the magnetic variables, we get something interesting. So just as before, as we crank the number of flavors smaller to be smaller and smaller, the electric description became more and more strongly coupled, and the magnetic description became more and more weakly coupled. Once we cross this boundary of 3/2 NC, the magnetic theory is really free in the infrared. So that's good, because it gives us a detailed description of the infrared theory. What we see at long distance are free quarks and gluons. They are not the original quarks and gluons. These are these magnetic quarks and gluons. And they have new gauge symmetry, and these are composite quarks. This is very surprising. It's very surprising because the point of view, the prevailing point of view until the 90s was that gauge symmetry is fundamental. The standard model is based on gauge symmetry. Gauge symmetry is the largest symmetry there is. Symmetries are good in principle, and gauge symmetry is a separate symmetry transformation at different points in space and time. This is fundamental, and this is good. This is the largest possible symmetry. Now we see that we can get such a symmetry without putting it in by hand. The original theory has one gauge group, SUNC, and the magnetic theory has a totally different gauge symmetry. And even if we didn't hear of duality, and somebody just told us what the solution of this problem is, the solution is that at short distance we see quarks and gluons of SUNC, and at long distance we see composite gauge fields. New gauge fields with their own gauge symmetry that was not there at short distance. So this gauge symmetry, which was supposed to be a fundamental principle of nature, being used in the standard model, and so forth, it appears that it can be emergent. We can have a theory that does not have these gauge fields, and these gauge fields come out of thin air, including the symmetry that accompanies them. In fact, there isn't a contradiction here. There is no contradiction because the name gauge symmetry is really a misnomer. Gauge symmetry is not a symmetry of anything. Already in Maxwell's theory, or in quantum electrodynamics, when we talk about the gauge symmetry, we are a little bit careless. One way to think about it is to fix axial gauge, and in axial gauge we construct the Hilbert space. The gauge symmetry does not act on the Hilbert space. Specifically, one of the constraints we have to impose on the Hilbert space is Gauss' law, that the divergence E is 0. In other words, the divergence E is the generator of the gauge symmetry. And what we say when we impose Gauss' law is that the Hilbert space should be gauge invariant. If we think of local operators, all the local operators should better be gauge invariant. So all the objects we talk about are only gauge invariant objects. We never discuss anything that is not gauge invariant. The local operators are gauge invariant, the Wilson lines are gauge invariant, all the operators are gauge invariant, and when we come to discuss the Hilbert space, all the states should be gauge invariant. For ordinary symmetries, operators and states in the Hilbert space and so forth are in representations of the symmetry. With gauge symmetry, we don't have any different representations. We have only one representation, only the singlet. So the gauge symmetry does not act on anything. So you could ask, why is the gauge symmetry there in the first place? If you look at your quantum field theory 101 book, you will see that gauge symmetry is needed in order to give a description of the system that is both Lorentz invariant and unitary. If you look at the quantization of electrodynamics in your favorite quantum field theory book, you will see that there are several different presentations of the quantization. Either you use a unitary gauge, which is not Lorentz invariant, or you use a Lorentz invariant gauge. So an example of a unitary gauge would be, say, axial gauge. It's not Lorentz invariant, but it makes unitarity manifest. Or you use a Lorentz invariant gauge, like Lorentz gauge, and then unitarity is not manifest. So in one gauge, it's easy to prove unitarity, and you have to work very hard to prove Lorentz invariant. In the other gauge, Lorentz invariance is manifest, and you have to work very hard with this Gupta-Bloiler procedure and all that to prove unitarity. So the significance of gauge symmetry is not that it's a symmetry, because it's not a symmetry of anything. The significance of gauge symmetry is that it gives us a useful description, a useful redundant description of the physics. So the gauge symmetry can perhaps be called gauge redundancy. We take a Lagrangian, we add all sorts of, we describe the system in a redundant description. Description that includes all sorts of gauge modes that are introduced only to make life easy. They do not propagate, they do not correspond to any physical observable, but they make the description easy. And different gauge choices make different properties easy to prove. But this redundancy should not be viewed as fundamental. Indeed, in this case, what we get at long distance are gauge fields that were not put in by hand. They reflect the quote-unquote gauge symmetry that is not a symmetry of the original Lagrangian. So this is one lesson from this whole thing. Gauge symmetry is not fundamental. In fact, it's not even a symmetry. We can get such composite gauge fields. Second thing we see here is what's elementary and what's composite could be a matter of definition or a matter of convenience. At short distance, the field M was a composite. It was bilinear in two quarks. At long distance, this description is good, and here M is elementary. So which field is elementary and which is composite might look different. The long distance observer would say, oh no, M is obviously elementary. And the short distance observer would say, no, no, M is obviously composite. Well, where can we tell the difference? For one thing, if M is elementary, it's not constrained by anything. Its rank, in particular, is not constrained. And if M is composite, if we think of it as being QQ tilde, its rank is constrained. So at short distance, the rank of M is constrained, because at short distance, it is a composite. At long distance, it behaves like a bona fide elementary field, whose rank is not constrained, thus resolving also one of the other puzzles we had here. Yes?
Could you explain what you said before about like how everything transforms as a singlet under the gauge symmetry? I mean, because superficially, I'm very confused by that. Because I don't know, like say you have an electric charge of a certain particle. I mean, like that is how it's transforming under the gauge symmetry, and that seems like very physical.
Okay. This is indeed a very confusing question, and I think it caused a lot of confusion over the years. And this can be answered several different ways. First of all, imagine the theory is strongly coupled, in which case we cannot even discuss the charge of the electron because the electron is an interacting object. We have gauge invariant local operators. The electron creation operator is not gauge invariant, right? Psi transforms. And therefore, it should not be considered. Its expectation value is 0, and it's not gauge invariant, so it should not be considered. What can be considered is an electron operator, localized here, and say a Wilson line coming out of it to make it gauge invariant, going somewhere at infinity. This is meaningful. And it might transform about under that part of the gauge group that acts only at infinity. But nothing acts on what's going on in the interior. So when you say gauge symmetry, there's a separate gauge transformation parameter here, and a separate one here, and a separate one here, and it's the same thing at different times, different generators. So we should separate the ones that act at infinity. We can discuss them soon. But those that act in the interior, really nothing is charged under them. So when you say that the electron has charge, you do not mean that it is charged under the gauge symmetry that acts here. Because under that gauge symmetry, it's obviously invariant. In order to make it meaningful, you really need to attach a line to it, this Wilson line. Now, if the system is strongly coupled, these Wilson lines carry infinite amount of energy, and therefore, we shouldn't even discuss such free electrons. This is the essence of confinement. We try to define a quark. We cannot. We have to say that it is at the end of a string, and the string weighs so much that there is no such free particle. When the system is in a Coulomb phase, and we have massless photons, we can define the charge at infinity. We cannot do that if space is compact, but if space is non-compact, we can define it. So that's what it is. The gauge symmetry itself does not act on anything, and there is no contradiction, and you should really go carefully through all the things you were taught. I got said that all the things that I was taught, and every single one of them is such that if it's correct, it can be rephrased in this language. And if it cannot be phrased in this language, it's wrong. So here is an example. The gauge symmetry, we all learned, I learned, and I'm sure you learned, gauge symmetry can be spontaneously broken. This is the essence of the Higgs mechanism. Well, this is slightly imprecise. It cannot be spontaneously broken. This symmetry cannot be broken because it's not a symmetry. If it's not a symmetry, it cannot be spontaneously broken. And it's not that the ground state is not invariant under the symmetry, as people sometimes say. The ground state is perfectly invariant under the symmetry. This is Gauss' law. Everything is invariant under the symmetry. So when we say that the gauge symmetry, and furthermore, you have the following point. When you learn about global symmetry breaking, you learn the following thing. In quantum mechanics, space is compact, and therefore there is never spontaneous symmetry breaking in quantum mechanics. You can only have spontaneous symmetry breaking when space is non-compact, because there you can have different ground states which are not in the same Hilbert space. In finite volume, all these states are in the same Hilbert space, but in infinite volume, if you have scalar fields with different expectation values, they are in different Hilbert spaces, because there is no local transformation from one to the other. We have to transform an infinite number of variables to move from one state to the other. The technical phrase is that they are in different superselection sectors of the Hilbert space. So in infinite volume, the Hilbert space breaks into separate sectors. Every single one of them is a separate superselection sector, and there is no local operator that takes us from one to the other. There is no finite time process that can move us from one to the other. Now let's contrast that, and we saw the same thing here when we talked about the flat directions. Every one of these points on the flat direction is a separate superselection sector in the infinite volume theory. Now let's contrast that with the case of a gauge symmetry. With the gauge symmetry, if we try to change the fields locally, there's clearly no notion of spontaneous symmetry breaking. Because for spontaneous symmetry breaking, you need to have an infinite number of degrees of freedom. You need to have this thing that two Hilbert spaces are orthogonal to each other at infinite volume. We clearly don't have that when all we change is the variable in some finite neighborhood in space-time. So this is the reason the gauge symmetry cannot really be spontaneously broken, because you don't have this infrared divergence that characterizes spontaneous symmetry breaking. And this is really the deep reason that when a gauge symmetry is quote-unquote spontaneously broken, there is no Goldstone boson. So the words that we often hear is that there is no Goldstone boson because it's eaten by the gauge field. But the precise way to say is that there is no Goldstone boson because it wasn't there in the first place. This mode that would have been the Goldstone boson is a gauge mode, and therefore it's not physical. Now, is the standard description that you learned in school incorrect? No, it's a very good one. And it's very useful, and correct, say, at the LHC when we study the weak interactions, because the system is weakly coupled. So the imprecise language that is being used for weakly coupled system is perfectly adequate. And it gives us the right answer, and you're never confused by it, and you can continue to use it. But you should remember that this language is not slightly imprecise, but very wrong by the time we are at strong coupling. When the dynamics is complicated and we have strong coupling, this whole language of talking about spontaneous symmetry breaking, spontaneous gauge symmetry breaking, becomes not just imprecise, it could lead us astray, we can give us completely wrong answers. Any more questions about this?
What does the equivalence between the two theories precisely mean? I mean, is there a dictionary between quantities on the two sides?
That's right. Yes, there's a complete dictionary between quantities in the two sides. Every local operator in one corresponds to a local operator in the other. And some of the correlation functions can be computed, and they are the same at long distance. At long distance, the two theories are equivalent.
So it's a statement about correlated green functions
Everything is the same. The spectrum is the same. Correlation functions are the same. Wilson lines are the same, etc. The whole thing is the same at long distance. And in this particular example, we can check a few of these things, but there are many more examples of that. So this is not an esoteric phenomenon. People have found similar phenomena for other gauge groups, SON, SPN, exceptional groups, different matter representations. This kind of duality is ubiquitous. It appears everywhere. And it even appears in string theory. And the whole notion of string duality demonstrates that we have many of the statements I made here are much more general. They're true in many other examples in field theory and in string theory. No, the whole way of thinking about it in terms of moduli space of vacua. At different corners, we have different descriptions. An exact formula nicely interpolates between two ends of the moduli space, or two different ends of the parameters, with different qualitative interpretations at the two ends, but it's the same formula. These things appear all over the place. And this phenomenon of composite gauge fields also appears to be ubiquitous. And so, yeah, this is there, and it's clearly generic. So to summarize what I've said so far, I said that there are two lessons to be learned from this whole four-dimensional gauge theory description that I'm now finishing. One is that some quantities can be computed, and the main tool in doing that is holomorphy or BPS, so the fact that they are invariant and they have supersymmetries or some other fraction of the supersymmetries. This is one class of techniques. And the main lesson we learn from that about the dynamics is the role of electromagnetic duality and its various cousins. So I gave you yesterday these two takeaway lessons, and I'm summarizing this discussion now. Before I change the topic completely, are there any more questions?
Is this true for the non-supersymmetric theories, like general?
I believe the answer is yes, and some aspects of it are known to be true in non-supersymmetric theories, specifically in 2 dimensions. And in 2 dimensions, there are tons of examples. In 3 dimensions, recently people found some similar examples of that. There are also similar phenomena in Chern-Simons theories. Some of them, if I have time, I will explain. In 4 dimensions, to the best of my knowledge, we do not have an example without supersymmetry, but I don't see an obstruction to finding it. I think supersymmetry allows us to calculate, and supersymmetry allows us to explore and to find such phenomena. I don't see any qualitative reason why supersymmetric theories, non-supersymmetric theories, should not exhibit this phenomenon. Because once a phenomenon exists in field theory, it could exist in other examples. We found it here, but it could also be elsewhere. I think it would be extremely interesting to find examples in 4 dimensions. But I warn you, it's not an easy problem. Many people spend a lot of time looking for that and couldn't find. Any more questions? So I'll change topics. Okay. If you think of questions later, please look for me. I'm around, and I'll be more than happy to answer. So we talked a lot about 4 dimensions, and I'd like to devote the rest of my talks here to 3 dimensions. And there are several reasons for that. First of all, because it's there. Same as going the outlook. We have supersymmetric theories in 3 dimensions. We should try and use the same techniques. We have field theories in 3 dimensions. We should explore them. So by and large, I think the attitude about physics is whatever you can calculate, you should calculate. Usually it pays off. Even if you think originally, well, it might not be interesting, every new result teaches us something. And sometimes it teaches us quite a lot. Another reason to be interested in 3 dimensions is that we have a lot of systems in the lab, mostly in condensed matter physics, which involve 3-dimensional field theory, and mostly in the context of statistical mechanics. And these might even have technological applications. So learning about 3-dimensional field theory is clearly interesting. There are also many new elements that exist in 3 dimensions that do not exist in 4 dimensions, kind of new knobs that we can turn, new parameters that we can turn and examine what happens as a function of them, and I'll review them here. And finally, we can view 3-dimensional theories as 4-dimensional theories compactified on a circle. So take your favorite 4-dimensional field theory and put it on, not on R4, but on R3 cross S1. And examine what happens as you dial the radius of the S1. So this way we should be able to interpolate between what we learned in 4 dimensions and what we are going to learn in 3 dimensions as a function of another parameter. And we should see phenomena similar to that. When the radius is small, the qualitative behavior is one thing. When the radius is large, the qualitative behavior is different. And we have a nice formula that interpolates as a function of the radius. And the thing I'm going to focus on, mostly toward the end of the last talk, is the role of this electric-magnetic duality that we learn in 4 dimensions. What's its role in 3 dimensions? And we can think of this 2 different ways. Way number 1, take the dual pair that we had, compactify it on a circle, and see what we get. What happens to duality under compactification? I should say that this was analyzed with Aaroni, Razamat, and Willett in a paper from about a year ago. The second aspect of it is that can there be new dualities? Are there new dualities in 3 dimensions? So we have seen, and I've argued, that this duality is ubiquitous in 4 dimensions. Is it also ubiquitous in 3 dimensions? We have many examples of that in 2 dimensions, mostly under the name of mirror symmetry and T-duality. What is the connection between all these dualities? And since we don't understand this mysterious phenomenon, whatever new insight we get could end up being helpful. So this is where I'm heading. But first, we have to learn some facts about 3-dimensional field theory that some of you might not know. Yes?
Can one ask the reverse question? Like, there are certain 3-dimensional theories, like mirror symmetry, for example.
Like what?
Like mirror symmetry for n equals to 4 theories.
Yes.
And there are not any known 4D dualities which are related to these, right? So can one turn the machine the other way around?
Well, you can ask this question, and I'm actually personally very, very interested in the answer to this question. I don't have anything useful to say about it.
But can your machinery be actually used for that?
Well, I'm going to do the same thing with n equals 2. So with n equals 2, I think I have complete control. With n equals 4, I do not.
N equals to 2 in 3D? N equals to 2 in 3D?
Yes. You were asking about n equals 4 in 3D. This is way, way above anything as far as the level. It's another level of sophistication beyond anything I said, and also another level of, higher level of sophistication of anything I will say. So I'll be happy to talk to you privately about this problem. But yeah, this is a very good question, excellent question. I'm very interested in, and I don't know the answer. These are usually the best questions we don't know the answers. Because the others we already know, so they're not really questions. So I think I should really review some things about three-dimensional field theory, because maybe you didn't learn them. And a lot of what I'm going to say is really ancient stuff, but then I'll move to things that are slightly more modern. So, in general, in 3 dimensions, it's easier to find interesting field theories than in 4 dimensions. And the reason is that these bounds that we had from asymptotic freedom are not present in 3 dimensions. So with these non-abelian gauge groups, we had some bound on the total number of flavors, because if we have too much flavor, then the theory is not asymptotically free. In 3 dimensions, we don't have such a bound. So we can have many, many flavors, and the theory is still interesting. And in fact, we can even study the theory in the limit of large number of flavors and expand in 1 over the number of flavors. There's always infrared. The theory is always interesting in the infrared. All these theories are UV free. Also, in 4 dimensions, we did not discuss abelian gauge theories, like quantum electrodynamics, the first example of quantum field theory. And the reason is that it does not exist non-perturbatively. Again, the same issue of lack of asymptotic freedom. So the abelian gauge theory in 4 dimensions does not exist. It could still be interesting, something to learn about perturbation theory and so forth, but this rich non-perturbative structure is not going to be there. In 3 dimensions, the abelian gauge theory is asymptotically free, and therefore it is interesting, and it exhibits very interesting and surprising properties, and it's even realized in the lab. So we have abelian gauge theories like the photon, when it interacts with some electrons. This is kind of the typical condensed matter system is an abelian gauge theory. Photons interacting with electrons, with materials, and that could do all sorts of marvelous things, give us superconductivity, superfluidity, Hall effect, boundary states. There's a whole huge field out there based on abelian theories. Next, there are many new coupling constants that exist in 3 dimensions and are not present in 4 dimensions. And I'll say a few words about them. So let me just enumerate. Chern-Simons terms exist in 3 dimensions. We can turn them on, and then we can ask, what's the behavior as a function of the Chern-Simons coefficient? There's also a parameter called real mass, which I'll explain in more detail. Specific to 3 dimensions, does not exist in 4 dimensions. And also, the gauge theories can exhibit new phases in 3 dimensions, phases that are not visible in 4 dimensions, like various topological phases. And this is a topic of huge interest in the condensed matter community these days. There's a whole field of topological insulator, edge states, and so forth, and it has even potential applications through the connection to quantum computing. So this is really something that is worth understanding. The second new element is these objects that are half BPS, objects that are invariant under half the supersymmetries. In 4 dimensions, this thing exists for particles only if we have 8 supercharges. So I've been talking here about n equals 1 supersymmetry. In n equals 2 supersymmetry, we can have particles that are invariant under 4 supercharges. With n equals 1 supersymmetry, we only have these local operators, like the chiral superfields. But we don't have particles invariant under half the supersymmetries. For that, we need 8 supercharges. What we can do with 4 supercharges, but it's not very common, is to have strings that are BPS. So these are lines that are invariant under half the supersymmetries. But we do not have such local operators, and we do not have, we do have such local, we do not have such particles. When we go to 3 dimensions, the situation is a lot richer. And it's richer because we can take this line, this string that is invariant under half supersymmetries, and wrap it on a circle, compactify the system to 3 dimensions, and get a BPS particle in 3 dimensions. So in 3 dimensions, with the same number of supercharges, 4 supercharges, this is known as n equals 2 supersymmetry in 3 dimensions, as I responded to a question here. With 4 supercharges, we can have particles that are invariant under half the supersymmetries. They usually come under the name of vortices. And our rule is that whenever we have something that is invariant under half supersymmetries, we can calculate. So this is one-line summary of what you can take from this. An object that is invariant under some supersymmetries, specifically half of them, we can calculate, we can say something intelligent about it. If it's not invariant under any supersymmetry, it's very rare that we can say anything intelligent. We can say something approximate, but not exact. So the next new element, as I said, lines can be BPS or invariant under half supersymmetries in 4 dimensions. They become particles in 3 dimensions. They become particles in 3 dimensions. Similarly, there are operators along lines, like Wilson line and 't Hooft lines, and they can become local operators in 3 dimensions. And specifically, I'll talk about monopole operators that are extremely interesting and have been this topic of a lot of discussion recently. So I'll define them. So let me start with the real masses in the links of them. In 4 dimensions, the basic representation of the Lorentz group is the spinor, the 2-dimensional representation. And we can write a mass term like that, or its complex conjugate. And I'm using Wessenberger notation. So the mass term is complex. It multiplies 2 Weyl fermions of the same chirality, or the other one here. The notation of Dirac fermions, we put the bars elsewhere, and then we're just relabeling what we mean here. So one of them, there's one linear combination with 1 and one linear combination in gamma 5. With gamma 5, I prefer to use well-defined representations of the Lorentz group. So this is what you're familiar with in 4 dimensions. In 3 dimensions, the Lorentz group does not have 2 SU2 factors, but instead there's only 1 SU2 factor. So in 3 dimensions, no difference between alpha and alpha dot. And therefore, we can still write these 2 terms, but we can also write a real mass term, psi alpha, psi bar, alpha. In 4 dimensions, such a thing would be a component of a vector. In 4 dimensions, if we take psi, we can contract the indices with sigma mu, and this is a vector. And therefore, we don't want to add it to the Lagrangian. This will break Lorentz symmetry. But if we put here the component 4, that does not participate in the 3-dimensional discussion, this is perfectly Lorentz invariant in 3 dimensions. So when we give fermion masses, there are 2 kinds of mass terms we should think about in 4 dimensions. The complex masses, which are essentially the same as in 4 dimensions, but there is a new term that in 4 dimensions is a component of a vector, and in 3 dimensions it's real. And before we ask what happens as we vary the masses, we make something heavy or light. Now we can do it in more than one way. We can turn on complex masses, or we can turn on real masses and get different phenomena. So imagine we have indeed a real fermion, and it is charged under U1. So we mean psi charged this is just 2-component fermion, psi alpha. So we can give it a mass. We cannot give the complex masses. So m psi alpha is not invariant under the U1. We don't want to do that. But we can turn on the real mass because psi and psi bar transform oppositely under the U1. In 4 dimensions, we cannot give such a mass term because it's not Lorentz invariant. But in 3 dimensions, we can. So we can study a theory of one doublet, one Lorentz doublet, one fermion, chiral fermion, charged under a U1, and give it a mass. Notice that these two things neither of these things can be done in 4 dimensions. A, we cannot couple such a U1 to a gauge field, because that would be anomalous. And second, we can't give it a mass. In 3 dimensions, we can do both. We can couple it to a gauge field, and we can give it a mass. So let's see what happens when we do that. So imagine the gauge field that we couple it to some gauge field, and we can think of this gauge field that we couple to as being either a background gauge field or a dynamical gauge field. The difference between them is whether we will later integrate out that gauge field also. But this is something we'll do later. So for our purposes now, we just take this fermion and couple it to a classical background U1 gauge field. So it just means that the kinetic term is d slash. So this is all Lagrangian. And since the fermion is massive, I might want to integrate out the fermion. This is not a question, right? It's a statement.
I'm just signing.
I quoted Dirac. So let's look at this theory. It's a free theory, so everything is calculable about it. And let's integrate out the fermion. When we integrate out the fermion here, something interesting happens. In particular, we can be interested in this diagram, 2 photons. And you can think of these photons as I said before, either dynamical or background fields. If it's a background field, it's the same as computing the 2-point function of the current. So this is the diagram that needs to be computed. And this diagram, gives us I over 8 pi, m over m absolute value, it's the real mass, AdA. So let me make a statement about Lorentz group first, and then we'll analyze the consequences. What does it mean to have rotation for a particle in 4 dimensions? In 4 dimensions, we have a massive particle. We go to the rest frame, and then we have a little group, SO3, for rotation. And the spin is tells us which representation of the rotation group we are in. In 3 dimensions, when we go to the rest frame, the freedom is just rotation in the plane, because space is 2-dimensional. We can rotate in the plane. And we can think of it as spin perpendicular in the direction perpendicular to the plane. And we can have different values for the spin depending on which representation of the rotation group we have. This fermion has 1 degree of freedom, and it has spin 1/2. That means that when we look at the plane, its spin is either rotating this way or rotating that way. So what determines whether the fermion is rotating this way or that way? We have only 1 degree of freedom, so it could do only one thing or the other. So something should tell us whether it's rotating this way or that way. And the answer is the sign of the real mass. So the real mass breaks parity. And when the real mass is positive, the fermion is rotated this way. And when the real mass is negative, the fermion is rotated that way. So when we talk about representations of the rotation group, they're labeled by a number, and spin s and spin minus s are not the same representation. This is unlike the situation in 4 dimensions. And indeed, when we take such a mass term that breaks parity, we integrate out the fermion, we end up with an effective Lagrangian for the background gauge field A, and this term breaks parity. So that's not surprising. Notice that the coefficient here is independent of the mass. It flips sign when the mass changes sign, and that is consistent with the action on by parity. Now, the normalization here is actually interesting. Writing here I over 8 pi, because this is the wrong normalization for a U1 gauge field. So this U1 gauge field is improperly quantized. We shouldn't be surprised by that. The fact that it's improperly quantized here reflects the fact that this theory, as it stands with the gauge field, is inconsistent. Because if we remove the gauge fields, we end up with a gauge theory that is inconsistent. And the inconsistency of this gauge theory, if these A's are dynamical, the inconsistency of this gauge theory really started its life with the inconsistency of the corresponding gauge theory in 4 dimensions, which is anomalous. But we don't need to think of it as coming from 4 dimensions. We can just be interested in this theory. And this theory is not gauge invariant, despite appearance. Because if we do a gauge transformation here, that looks okay. This looks gauge invariant. But this one is not. If we put this theory on a complicated 3 manifold, the fact that the coefficient here is improperly quantized is the statement that this theory is not really gauge invariant. And this can be stated many different ways, more sophisticated and more correct, but the bottom line is the same. This theory is not gauge invariant. So what should we do about it? Well, this is an anomaly, but it's not a devastating anomaly. Because an anomaly is a devastating anomaly is an anomaly that there's nothing we can do about it. Here, there's a very simple cure. Imagine in the original theory, we add here another Chern-Simons term, which is also improperly quantized. Then we can just copy it here. And now the Chern-Simons term is properly quantized. The technical term for this thing is the statement that we add here a local counterterm. So this theory is not gauge invariant, but we can make it gauge invariant by adding a local counterterm. Another way of saying it is that if we integrate out the fermions here, the answer is not gauge invariant, but if we add a local counterterm, we make it gauge invariant. But this has interesting consequences, because we had a theory here that was not gauge invariant, and therefore we had to add a term. We also had the freedom to add here any integer I over 8 over 4 pi a dA. But we must add half integer here, kind of half of this unit. Notice that as the mass changes sign from being positive to negative, so imagine we set n to 0. So if m is, say, positive, this is 1, and this is 1, so together we get a non-trivial Chern-Simons term. When the mass is negative, this term exactly cancels that one. But even when the mass is 0, either positive or negative, we still need to add this term for gauge invariance. Or we need to add this term here. This is a characteristic situation with anomalies. One might say that when m is 0, the theory is parity invariant. This theory appears to be parity invariant when m is 0. But for gauge invariance, we had to add this term that breaks parity. So this is characteristic with anomalies. We have 2 requirements about this theory. One, we want it to be parity invariant when m equals 0. And second, we want it to be gauge invariant when we couple it to gauge fields. And we can satisfy one or the other, but we cannot satisfy both. We need to sacrifice one of the 2. And the one we sacrifice, in this case, is parity, because we think that gauge invariance is more sacred. So what the statement is that even for 0 mass, we must add this local counterterm to make the theory gauge invariant. But that means that even for 0 mass, the theory is not parity invariant. And since I don't want to be killed by Hiroshi, I'll stop here.